Welcome as we go along, and we are in the last lap of the course. That is something we have to understand, that we are actually gradually coming up to the climax. We are almost near the peak. We were climbing a mountain and we were near the peak. So, with these two lectures we will now introduce surface integrals, and then we will start what is called integral theorems in vector analysis. So, this integral theorems of vector analysis. So, what is not vector analysis, you can say multivariable calculus, whatever you want to say. These theorems actually unite all these things that we have learned, they link all of them. Is there any link between divergence, curl, gradient that we have learned in differentiation? Is there any link between the integrals that we have learned, line integrals, surface integrals, other multiple integrals? What is the link? All of these ideas are linked in that particular form, and they have a lot of applications in the physical sciences. And so, this part of mathematics has got a huge application in physical sciences, and many questions have come because you are trying to understand problems in physics. So, today our first thing that we want to learn about surface integrals is not surface integrals as per se, what we call surface integral, but we will talk about integrating a scalar function over a surface. So, you see here written down here on the screen that there is a function from R3 to R, which is a continuous function, and there is a surface parameterized by phi. So, the surface is given by coordinates. So, basically uv is mapping to some and zuv. So, this is the parameterization which we have been speaking about. So, by this time you have got some handle on this idea of parameterization, some hold rather. Now, what do I mean by this integral f ds? So, let us try to understand integral f ds. So, there is a domain D which is always there, and integral f ds. So, because I have parameterized, you really know that integral f ds is nothing but, and I am not going to do any calculations with you here because calculations are all done. So, we are not going to get into this issue of calculations. So, let me see how we proceed, and then I will keep on adjusting the number of lectures. Possibly I have to give some more lectures on integral theorems. So, maybe I will cut this surface integral lecture in one talk. So, let us see what happens. So, this simply means that what is ds? We already know about ds. This means f x y z into norm of phi u, and you know what is phi u, the vectors phi v, this norm into du dv. That is what is the meaning of this integral. So, I am not going to write down the expressions of phi u cross v in terms of those Jacobian determinant of those Jacobians, which you know already. So, example where which talks of something called a helicoid. So, I will just tell you what a helicoid is, and I will just draw the helicoid and give you a parameterization, and then I will just leave it to you to find that integral. So, let me just first start giving you a picture of a helicoid, or rather let me show you the parameterization. So, I have a curve, a surface S, parameterized as x equal to r cos theta. So, parameters here are r and theta, the u and v, y equal to r sin theta. So, they are lying on the circle, and z is equal to theta. So, what kind of a stuff it would look like? That is the question. So, it is very difficult to draw an helicoidal surface actually, but you can go and check just in type Google helicoidal surface. There is a Wolfram who has this software Mathematica, they have drawn it. It is a kind of very strange kind of 3D surface, and I do not think this is a good idea to even make an attempt to draw it. So, helicoidal surface looks like kind of like this, comes up. I am just kind of making an attempt. I am just making an attempt to draw it. So, you see how complex this structuring looks. So, this is one sheet and this is another sheet which is mixing up, and this is a different sheet. And this is completely a different stuff. You can see the helicoidal structure here. It is very difficult to make a drawing actually. I had a drawing done before I came here, and so I am just looking at that drawing and trying to draw here, because it is a very difficult structure. You use computer algebra based software like Mathematica or Maple and draw this. You will have a lot of fun doing it. I assure you that you would have a lot of fun doing this thing here. So, here I am asking you to find the integral of, say, if you want to do something is so the problem given as an example in the book, they ask you to find an integral over this. Obviously, instead of x you will put u and v. So, what is f here? So, f will be replaced by r cos theta, y is replaced by r sin theta, and z by theta. So, root over x square plus y square plus 1. So, then this is equal to root over r square plus 1. So, similarly, if you compute this norm phi r cross phi theta, take the norm, that would also be root over r square plus 1. That is the interesting part here. So, then the integral, I leave it to you to calculate with dr is actually integral f. You know the domain now, r is between 0 and 1. Let us, of course, r let me put between 0 and 1. This is the drawing from r between 0 and 1, and theta is going between 0 and 2 pi, because we have taken a circle of radius r. We are going within that zone. So, we are also changing r. So, change r, but as you change the theta, what is, so here is an r. So, here, so there are various thetas, and based on that z is coming. So, it is like this. So, it is a kind of helicoidal structure that goes up. So, here you have f of phi u cross phi r cross phi theta dr d theta, and the answer that you will get is 8/3 of pi. It is quite amazing that such a complex looking object, right. So, it is a complex looking object. So, as you move to theta from 0 to 2 pi, this is the whole thing that it will give. So, such a complex looking object would have such a simple looking, so it is irrational, the number, that is also one point, 8/3 pi is irrational. So, but such a complex looking object would have such a simple looking expression for the area, and that is what the beauty of mathematics is, and that is the power, that you can really understand such complex shapes using mathematics. And now we come to what we will call actually the surface integral. It is the same story, but a little different than what you have learned in line integral. So, in line integral you had a vector field f1i vector, f2j vector, f3k vector, where each fi was a function from R3 to R. So, f can be also viewed without writing the arrow form, because we will not write in the vector form, as a function from R3 to R. So, it is a vector valued function. So, what did you learn? That if you take a small arc length, kind of dr basically. So, f dot ds with a small arc length over a curve, this is what is called the line integral. So, the same idea, can it be done for the surface? So, that would give me a surface integral. So, instead of integrating over a curve C, what if I take this vector field f and integrate it over a surface? So, I am now trying to define an integral of this form f dot ds. So, maybe I should put the vectorial form with ds, and if you want with f also, just to make it look more. So, this is what I want to do. You may not put f here, you can put here, because I have already started putting the surface area vector in that form, ds vector. So, I am just trying to put f also to keep a kind of symmetry. If you do not want to put, do not put. So, it is understood that it is a vector valued function. So, that is what is, I am trying to understand what is the meaning of this. But if you look at it, what is the surface integral, or what is this ds vector? So, here is a small elemental surface area, here is your normal vector, and the ds vector is the unit normal vector. This is a unit normal. So, it is n vector ds. So, ds is the value of the surface area, and this is the ds. An area vector is always perpendicular, because area of parallelograms is given as cross product. So, this is your, so n hat. So, ds is actually along this direction, that is your ds vector. So, I can write this f dot n vector is unit normal. So, because it is whenever I will talk about a unit normal, I will give n hat. So, because I hat, j hat, k hat, these are all unit vectors. So, whenever I am talking about a unit vector, instead of putting an arrow, I will put an hat, just to signify that it is a unit vector, and I need not keep on repeating that it is a unit vector. So, this is what is the meaning of a surface integral. But how do you now ask me, then why did you teach this at all? Because if you are ultimately going to talk about this, but I say that I have taught you that, because I will use that idea, that type of operations to actually compute surface integrals. So, this is what I would try to show you. So, now we will see that how can we use this idea of parameterization. So, take a problem from the book and try to see how we can handle it. Now, there is a problem in the book which says that, so here is the problem, I write in black. S is the surface of a unit sphere and it says that let F be a vector field and Fr be its radial component. So, Fr is its radial component. Radial component means, I will tell you what, Fr is its radial component. So, here I have my unit sphere. So, I draw the axis in blue and then I will draw the sphere in some other color, maybe maroonish. So, at any point here, on the curve, which is x, y and z, so here any point on this sphere, so the vector field f that is there, that you calculated that point, f of x u v, y u v, z u v, there are two components. One component can be taken along a tangential direction and one along a radial direction. So, in the direction of the radius towards the center. So, this is the this is your Fr component, and of course, the magnitude of Fr is Fr. And what the problem says is that prove that, problem says the following, show that f dot ds is 0 to 2 pi, 0 to pi f r sin phi d phi d theta. So, this expression can be possible if you express the coordinates on the surface of the sphere in terms of what is called the spherical coordinates, right, that is very important. So, let us see what happens if we take the spherical coordinates. So, if you take a spherical coordinate, spherical coordinates. So, brother, I should write parametrization through spherical coordinates. Actually, this FR vector that you see here is basically minus of FR value into R vector. That's R vector, where R vector is xi vector, yj vector plus zk vector. So, now we will parameterize through spherical coordinates, and in this parameterization through spherical coordinates, you know what is how to parameterize. So, if I parameterize to spherical coordinates, I have x is equal to cos theta sin phi. You have to understand here my radius is fixed. Here I have taken a unit sphere. So, radius is 1. Actually, my radius is fixed. So, in this case my radius norm of R is 1. So, mod of FR is FR. Mod of vector FR is just this FR. So, this is actually the radial component. So, x and y is given as sin theta sin phi, and z is equal to cos of phi, r cos phi, which you know. So, what we have to do? Here I have my x uv, y uv, z uv. So, my phi theta phi is cos theta sin phi plus sin theta sin phi plus cosine of phi. So, here I am going to write ds in terms of that. So, ds vector would be in terms of that phi cross phi u cross phi v. So, my phi u is equal to minus sin theta, and this is cos phi k vector, sorry, I vector, j vector, k vector. So, minus sin theta, so phi u I would not say, phi theta I would say, phi theta. So, theta means I have theta here, I do not have theta here. So, minus sin theta sin phi I vector plus cos theta sin phi j vector and plus 0 k vector, and phi of small phi, capital Phi of small phi is, now you take this cos theta cos phi I vector minus plus sin theta cos phi j vector minus sin phi k vector. So, I have this phi u cross phi v calculated, which I am not going to have separately checked. It can be so phi u cross phi v turns out to be the following. So, let me just write down the expression of this, so that I do not which is already I have checked up and calculated, is that this expression turns out to be minus sin square phi cosine of theta I vector minus sin square phi sin theta j vector minus sin phi cos phi k vector. Now, what is direction of f? Now, f vector can be decomposed into two parts. you can always do for a vector. One is the tangential part at a given point x, y, z into tangential part, and another is the radial part. Now, when I am doing f dot n, this n vector is only along the radial part, the n vector does not have any tangential part. So, this would just become fr dot n vector. Now, what is n vector by the way? N vector is nothing but, so it is decomposed into two parts, fr plus fr dot n vector. So, it just becomes fr dot n vector. So, n vector does not have any radial part. So, when you are taking an f dot n, we are writing an f dot n, that also must have a radial part, but n vector does not have a radial part, a tangential part. It is along the radius, so it has a radial part. So, f dot n here, if you decompose it into tangential part plus radial part, so whenever you have some at a point f vector, if you have an f vector given and at any point on the surface, it should have a tangential part and it should have a radial part, or the radial part could be. So, this is my f vector. So, this is the radial part and this is the tangential part. Okay. So, I am writing it like this. F, it depends on what is the orientation of f here. Okay, the f orientation could be different. So, there are two parts, fr dot n vector. Now, what is n vector? So, what is fr? So, fr is fr to r vector dot n vector. So, n vector, if I go by my rules, then it can be written as phi of theta cross phi, capital Phi of small phi by norm of the same vector, phi theta cross phi of small phi, this into d theta, d phi d theta. This is n vector, this n vector into ds, which is, so my integral, surface integral is f vector into ds vector, which is integrally written as integral s f dot n vector ds. Now, what is ds? ds we have already learned, in this particular case should be phi theta cross phi of small phi into d theta d phi. So, so this is your n vector. So, what is your, so your integral s f dot ds vector is integral s, what is your f? F is nothing but r into, when you are writing, so when you are writing f dot n, so what is your f dot n? It has become fr to r vector dot phi theta cross phi u by norm of phi, sorry not phi u, phi small phi theta cross product phi, capital Phi of small phi norm, this thing into ds, which is norm of phi theta cross, which is the ds. Now, it is not the vector ds, it is the scalar ds, n dot ds, n vector ds is the ds vector, which we have already discussed here, you just see it here in the board. So, it is phi of u, right. So, this thing into d theta d phi. Now, these two cancels, assuming that these are non-zero, of course, that is the standard assumption, and it is non-zero in the case of our our particular problem, the surface of the sphere. So, what I get here is integral S FR vector, it should be a scalar multiplying a vector. So, FR vector dot of, sorry, not FR into R vector, FR into minus R vector. So, I am coming in the direction opposite to, if you want to come in the direction opposite to minus R, then minus R. So, or if you keep as a FR vector, then let us see what it comes. I am just seeing what, so FR into R vector, I am taking FR into R vector as the, you can take it depends on the type of force you have basically. FR into R vector, let us take it along the outward direction. So, if the force component, so if FR into R vector into phi theta cross phi small phi into d theta d phi. I just want to tell you that now once you have this R into, now you have to do R into now what is R here? R here is xi vector plus yj vector plus zk vector, and so in this case R vector is cos theta sin phi I vector plus sin theta sin phi j vector plus cos phi k vector. So, if you do the, now if once you have this, now if you do the inner product, it gives me minus sin phi. Okay. So, what do I have? So, I have integral S f dot ds is equal to integral S fr minus sin phi d theta d phi. So, you know what is the angles things, how you know where theta varies. Theta is varying from 2 pi to 0 and phi is varying from 0 to pi. So, here sin phi I can take the phi, integrate over phi first. So, 0 to pi, 0 to 2 pi minus fr sin phi d theta d phi. So, I believe that there would be a minus sign here in the problem. I do not know why they give it. I do not understand why they had not put a minus fr. There should be a minus fr. So, this is a calculation of a surface integral. Now, certain things has to be understood when we are talking about surfaces. It is called orientation of surfaces. So, here is the surface and let us consider a point, let us consider a small elemental area on the surface, and from one of the central points here, center point, I draw normal. So, you see this surface, you can say okay, I can draw normal on the other side also, which is minus of a hat. So, it depends. So, the surface has a orientation. So, when I am talking about oriented surface means I can say which is outside of the surface, which is inside the surface. For example, here I can say this part is outside, while I can say this part is inside. This idea is somehow slightly important if you are calculating surface integral. Just like in line integral, if you move along the curve from you have a curve from A to B, C, a curve joining A to B. If you move from A to B, you have a value of the line integral, some value, but if you move from B to A, the value will change, it will become negative. So, orientation matters, which direction you are doing. So, here orientation, whether you are looking at the surface from inside or surface from outside, that would matter. So, a oriented surface is a two-sided surface. And oriented surface is a two-sided surface, and we can decide which is outside and which is inside. We can fix the outside and inside of the surface. So, you can now you say that, for example, the n vector, when n vector is positive, I say it is outside, in this case n vector is negative, I say it is inside, but all sides. So, you see, so if I move n vector along this surface in the positive direction, this will continue to remain positive. So, for example, if I have this surface here, so if this is my n vector and I am moving it, so it continues to point in the outside direction. So, here I put it here, this continues to point in the inside direction. See but there are certain surfaces called Mobius surfaces, like I can show you by some demonstration, an interesting surface. Cut kariye. So, now I am going to introduce what is called a one-sided surface or a Mobius strip, just for your curiosity that every surface need not be two-dimensional, but two-sided. So, take a paper, it should be a slightly longer paper, and give it a 180-degree twist, and then attach it. So, it is something like this. So, if you start say from a point here, so from a point here, if I point outward, so I go along this pointing outward, pointing outward, pointing outward, pointing outward in this direction, and then suddenly here I come and point inward. So, it is my vector which was pointing outward, it is pointing outward from here, and if you go like this, you put your hand like this and move it, and then you have come to the inside. Basically what you feel, come to the other side, your direction which was when you come back to this direction at this point from where you have started. So, you have started you are pointing in this direction. So, now move, let us move. So, here you see your finger direction has changed. So, means for a two-sided surface, if I move, if on a surface of a sphere, if you take a normal vector and keep on moving it, then when you come back to that same point around the circle, you will be pointing in the same direction. Here I pointed along the opposite direction. So, it is an example of a one-sided surface called Mobius strip, and so there are these kinds of things in mathematics. So, and this is pretty interesting that every sided is not two surface, but we here we will largely work with two sided surface which has an orientation. So, a given parametrization phi phi is called orientation preserving if the unit normal, which is given as phi u cross phi v cross phi u cross phi v. This so given a parametrization phi, this is called orientation preserving. Of course, you are assuming that if, sorry, I should write, maybe I should write it in a much more better way than what the book has also written. If phi is not a 0 vector and the n vector agrees with that for a given orientation, n vector agrees with that for a given orientation. So, if I have given an n vector in a given direction and that is what I think is my outside direction, and if the n vector turns out to be positive, then n vector is called the orientation preserving vector. If n vector turns out to be negative, it is called orientation reversing. If n vector is in the opposite direction, if n vector is in the opposite direction, then it is orientation reversing. Try out this for a unit sphere. So, when I am putting n vector, so this is my outside. You know, we intuitively understand what is outside of a sphere. So, you know what is outside of a sphere. So, this is another n vector. Now, is this, so suppose now I parameterize it. So, how do I parameterize a sphere? So, I parameterize a sphere using spherical coordinates. So, I parameterize it using spherical coordinates. So, I have my phi u v here or theta phi here. So, if I do this and you know what is phi, so it is cos theta sin phi I vector plus sin theta sin phi k vector and cosine of phi j vector. And you know that what is phi of theta cross capital phi of small phi turns out to be something like this. Cos theta I vector minus sin square theta sin phi j vector minus sin phi cos phi k vector. Now, if I take the sin phi out, the remaining what I will have is minus r vector. So, basically it is minus r vector is sin phi into r vector minus sin phi the scalar into r vector, that is the. So, what I have here my normal which is phi of small phi capital phi of small phi. So, it does not matter what is this. So, if you take the norm of this is nothing but the radius sin phi, radius into sin phi. Sorry, theta. So, if this is my normal vector, the normal vector turns out to be minus sin phi r vector by sin phi r. So, it turns out to be minus r vector by r, and that is has a negative sign, it is pointing inwards. So, my parametrization, the parametrization in spherical coordinates, this parametrization is orientation reversing. So, if I have two parametrizations phi 1 and phi 2 giving the same surface and both of them are orientation preserving, then phi 1 f dot ds is equal to phi 2 f dot ds. Suppose phi 1 is orientation preserving, but phi 2 is orientation reversing. Phi 1 is preserving and phi 2 is reversing. Then the whole game will change. So, what you have learned about line integrals appears to be true in the case of surface integrals. So, basically I have clubbed both my lectures on surface integrals into one, hoping that I will have some more time to speak about Green's theorem, and that is why I did it. So, Green's theorem will be done very carefully, and with this I end my talk.